all of us are grateful for the effort by our science team, but of course, the project itself. But anyway, this is just some of the people that have been helping myself and the rest of the team put the material together. Next chart, please. Oh, do I work that? No, you'll do it. I'll do it off here? Okay, let's see if I press the right one. Okay, well, most of you have heard me talk about, could we have the lights down a bit, please? Lola, it's a multi-beam laser altimeter, 5 beams as such. Each spot within the beam is 25 meters from every other spot. So it's a long, thin profile. We got the lasers operate at 28 hertz, and there are 5 spots. So we're collecting measurements in principle at about 140 measurements per second, and we've been operating pretty much continuously. Let me see if I've got the right chart. Okay, yeah, the stats for Lola are like this. We've been operating continuously since something like July the 13th, nearly 2 years ago, or just over 2 years ago. We collected somewhat over 4 billion altimetric measurements from the instrument, what I call good ones, because some we do have to reject, maybe 1% or so. The performance of the lasers right now are about a billion measurements on the first laser. We've been ping-ponging them backwards and forwards month by month, but in fact, we designed them each to be about 1 billion measurements, and they're both behaving well, and one has surpassed that. So we're pretty comfortable with what we've got. Each of the measurements is nominally about 10 centimeters quality on a reasonably flat surface. The spots are 5 meters in diameter. And at the pole, we're a little under 50 meters, a measurement of every 50 meters on average. And when you get closer to the pole, it's down to about 35 meters squared. Okay, well, 3 data sets we normally or routinely produce. First is topography, and I'll say a little bit about that, but more about slopes and surface roughness. Slopes comes basically from the topographic measurements with scales of nominally about 25 meter slopes, but we average some in many cases. And the surface roughness says here 25 meters to 100 meters, but what I'll be showing you all today will be on scales of 5 meters, because that's the size of the footprint. The laser altimeter provides this pulse that goes out at some measure about like this. It comes back wider than that due to the topography within the footprint, and we use that for surface roughness. Okay, in terms of average of measurements we just collect linearly one more pass all the time, and the resolution gets slowly better in longitude. A long track, it's about 20 meters resolution all the time as we're moving along the orbit. Across track, it depends on the number of tracks you have, and this increases linearly. Right now, that average is around, or the mean is around 640 meters at the equator, which is the largest area. There are gaps. You can see it's by the chart here. It's not a uniform distribution, and so just recently we've started to try and infill the larger gaps at the equator with off-nadir sloughs in collaboration with LROC, just to make sure we don't interfere with their own, excuse me, their own off-nadir measurements. Okay, at the pole, because we're up at the pole there, and as Mark pointed out, we do get a very high resolution there that they can add to their global topography. And here we're running around 20 to 10 meters, depending on the particular area we're talking about. The North Pole is on the left, and the South Pole is on the right. Shackleton is the major crater right in the middle there. In the same way, we can, from all this topography, derive, of course, areas of permanent shadow, and you've seen many of these before. On the left-hand side is the North Pole, with many, many more areas what appear to be permanent shadow over an 18.6-year period, and a smaller number in the north, but a larger area overall. So the dominant shadowing is, in fact, in the south, as we have really known, but it's 2 completely different populations. Now, using these, we can produce a movie didn't get transferred. There's a movie in here, but you've seen this kind of thing, I think, before, in which we can produce from the topography. Now, one of the interesting things cropped up recently is that we think we're doing quite well, but LROC has found some circumstances in which where we think we're seeing permanent shadow, and then for a very short while, there's illumination that they catch that we don't. And so it's a matter of how well you can model the topography, and it is a test of a rather extreme test of what you can actually model with the topography. We think we're doing it down at a few tens of meters right now. Okay, up in the polar regions there are several important craters, one of which is Shoemaker, and it's very interesting because besides being almost impermanent shadowed, is one of the crater really in the north there that is showing this this presence of hydrogen. And other craters right nearby, almost identical, do not show anything at all. This is Shackleton you're looking at right now, the floor of Shackleton. The features or the parameters are on the right-hand side there, has a depth of about 4.5 kilometers. As such, and it's quite large at about 51 kilometers in radius. The next one is Hawthorne, which is very close to it as well. This shows no anomaly in hydrogen whatsoever, and it is very similar. It's a little rougher on the floor of the crater that you can see here, and these are contours at about I think 50 meters, as you can see. The next one in that same region is in fact Faustini, all essentially in the same region. Within kilometers of each other, actually, a little smaller, a little shallower. Again, no hydrogen increase whatsoever. And if you look at them in a comparison of their topographies, and these are just cuts through the topography in the same particular direction from the pole, and they all look very similar in many ways. And on the top row, they're all on the same level in terms of the origin of zero. And although this is out of scale, if I might say so, you get a feel for what is going on when you fit a curve to parts of the orbit, which is parts of the crater wall, to give you some idea of maybe how deep that crater was at the time of impact. You put them all together down the bottom down here, and you still find they're all got about a kilometer, looks like a kilometer of fill in this very simple modeling approach. But it's only Shoemaker, the one in the middle, that has this hydrogen evidence of hydrogen present. Okay, looking at this in surface roughness, we're looking at 5 meter scales now. This is a pulse comes back. We measure the broadening of the pulse. We deduce the roughness. All of these look very similar in many respects. You might argue in the center of the circle there's evidence that it's a little rougher than it is outside, but it's pretty benign compared to some areas. Okay, this is the floor of Shackleton. I think some of you may have seen this before. This is actually it's a very smooth area with long undulations in there. Smooth in the sense of 5 meters. In great detail, it's in permanent shadow. We see it extremely clearly with the laser altimeter. This is the Apollo 5 landing site. I'm showing you here a profile that runs across Hadley Rill. The 5 profiles are shown at the top in the different colors. The individual spots are there. They're at about 50 meters in each colored line. Below that, you can see the slope on the surface, which gets up to 35 degrees. And lower down in the blue, I think you can, not very well, or the purple, you can see the roughness that we see at about a little under 5 meters. But remember, this is a little under 5 meters. Moving right along to more of this, the Anastacious Crater, which is quite high in latitude. You see this red line through the middle, which is a profile, and on the right-hand side of the image, you see the actual slopes. And again, I hope you can see with the colors that we are frequently getting up to 30 or 35 degrees in the slopes over distances of 25, 50 meters and thereabouts. The roughness is running around, on the second chart down, around 4 meters, as high as, but frequently around 1 or 2 meters. And in the lower chart, you can see the way the 5 profiles in the different colors all lie pretty much not exactly on top of each other. They shouldn't, because they're 25 meters apart as they go down the slopes of the crater and up the other side. And so you can get the undulation of the surface as we move through. Now, Anastacious, if you look at it, it's now just in the slopes on 25-meter baselines. You see the left-hand side. You clearly see the ridges and the rings around the crater and inside the crater, for that matter. And on the right-hand side, you see the surface roughness. And the surface roughness here, it is rougher on the inside than around it. And so this crater is one of those that is demonstrating quite a big difference between the inside of the crater and the outside. That's not always true, and I think the South Pole Aitken crater, thank you. The South Pole Aitken crater shows the topography on the left, shows that kind of flooded area in the middle. If you look at the baselines down the slopes on the baselines at the bottom there, you can see the outline of the crater very nicely. But if you look in the top right-hand corner there, you see the slopes and see the roughness, and it's pretty benign all the way across, whether it's inside or outside of the crater, no matter what the elevation is. If we go to another crater, which here it comes now, which is Tycho, which I think some of you have seen. Mark showed a very nice image of the central peak. This is one of those that shows, again, the same evidence in terms of the slopes and the character that you can get just from the slopes on very short baselines. But the roughness, according to us, inside the crater is very severe compared to outside. And here we're talking about numbers within 5 meters, we're talking about numbers of 5 meters for the roughness. So it's clearly rocky in some form or other. And this is perhaps one of the severest in a sense that we have seen so far. Okay, Alphonsus crater is another one of those which is rather benign. And this is the story of many of the craters that we have looked at in some detail, is where we get a great topographic image, we get a well understood slopes and baselines showing the character, and then inside and outside the craters we see at a 5 meter level just absolutely no difference in terms of the roughness of the surface at all, which presumably says something about the age and the way the surface of the moon in that region has been modified over time. And there's another one. Oh, okay, yeah, the Apollo 16 landing site here. I do show this here. This is also one of those very smooth ones, and the 5 meter spot size. We did land there. That's probably good. The baselines are revealing in the same way that they have been in the others. That shows you a little bit more clearly what's going on in and around the craters. And I think, Mike, that is probably, yeah, there is a summary, which the topography is at 10 meters to 1 kilometer. I'm not showing you the global stuff. I've been showing you the smaller areas. And the slopes on 25 to 50 meter scale and roughness are all showing slightly different pictures of the surface of the moon. Interior of craters, some are much rougher than the outside, and some are just the same, inside or outside. It doesn't matter where you look. And that's the end of it, Mike. Okay? Thank you.
Any questions for Dave?
Will you ask, is there a correlation between the roughness and the diviner rock abundance? Is that what the question? If I do not know the answer to the question at the moment. It's one of those things that we need. Oh, it's a comment. I'm sorry. Okay, thank you. Well, great.
Another comment?
Do I see any difference in, I'm sorry, I didn't get the...
In the return at the terminator.
At the terminator. Yeah, we do, but it's got nothing to do with the surface. It's got to do with the way the altimeter is behaving as it moves across the terminator. I think some of you know there's what we call a Lola anomaly, in which as the spacecraft moves towards the terminator, the temperatures get very cold on the outer skin of the spacecraft, and the blankets in particular. And the blankets that surround the laser altimeter contract, very small amount, about 50 microns, no, actually a few hundred microns, I beg your pardon. But the net result is it squeezes the instrument, and it pulls the transmit beam slightly off of alignment properly for the 5 detectors and 5, and they have to match up. And what happens is they move. And one spot moves into another one. So there is a difference, but it's of that kind. It's not what I would call lunar origin, basically. It's a spacecraft and an instrument issue.